So welcome everybody, and I am Angela Paholic, and I'm the Member Services Manager with the St. Alberta District Chamber of Commerce, and we're so thrilled that you have joined us today for our webinar, Lunch and Learn, what is Geotechnical Engineering? And with us we have Zaber Rayman. See, I should have said
Raymond.
Raymond. And Zabir is a dynamic professional with 23 years of experience in civil and geotechnical engineering field. His career highlights includes numerous positions with leadership and engineering roles, which were held in major international consulting companies. He is the president of ESPIRA Engineering Limited out of St. Albert, Alberta. He is a board member of the APEGA, St. Albert ESAB, and IDEA. He is a proud resident of St. Albert with his lovely wife and 2 daughters since 2012. He has 23 years of geotechnical design, materials, and engineering project experience, including project management, bid preparation, foundation analysis, and design. His experience also includes concrete mix design analysis, reinforcing steel inspection, lime stabilization, construction monitoring, and compaction. So with that, I am going to hand the webinar over to you, and away you go.
Thank you, Angela, and thank you, St. Albert Chamber of Commerce, for organizing this. This is a great opportunity for us to learn about geotechnical engineering. And good afternoon, everyone, and thank you for joining us today. This presentation will include a lot of visualization and some videos, I hope, just to make understand, what the geotechnical engineers do, so you can see in the videos instead of just me talking about it. So, what is geotechnical engineering? Geotechnical engineering typically deals with soil mechanics and soils and foundation design parameters. This one takes consideration of earthquakes, landslides, sinkholes, rock falls, etc. in different parts of the country and around the world. Now, anytime you want to do a project, build a project like a roads or high rises or commercial buildings, etc. First thing you probably need is one of the very first essential thing is the geotechnical engineering. Can we build what we're planning to build in that particular site? So that's what, kind of in a nutshell, what geotechnical engineering is. Now, geotechnical report is generated for different audiences, so it means different things for different readers. For example, for an owner, what does the owner mean to owner? Owner, if someone is deciding to buy a land, so a lot of times they get geotechnical engineering professionals involved to make sure that that land is suitable for the purpose of their purchase. Now, developer, they want to build high rises, things like that. And for example, I mean, there are commercial buildings or residential buildings. So they want to know what are the challenges they will face. So they hire the geotechnical engineer to kind of assess, and that report kind of explains that if that land is suitable for the purpose. The architect, a lot of times the owner, when they purchase land, they hire an architect to hire all the other consultants and manage them. So one of the principal things that architectural engineering architecture does is hire a geotechnical engineer to make sure that, again, the foundation would be feasible and it'll be kind of economical for everyone, and so everybody would be winning at the end. So a lot of times the structural engineers, the other engineers need the information from geotechnical engineers to design their foundations. They look at the options. What are the most economical option? And that's what the geotechnical engineer teams up with the other engineers, for example, the structural engineer, to make sure that the foundation is feasible and economical. Now, the contractors, before they go into a site, so they want to make sure that they do an estimate, and their estimate based on like what type of soil they have. Is there a lot of organics in that site, or there's topsoil? How thick is the topsoil? So this geotechnical report provide those information to those contractors to kind of get a better handle of things, a better understanding of what they're going into before they go into construction, or what type of water table they're going to be dealing with, etc. So municipality, before any project goes ahead for development permit or to be for development permit, so part of the requirement is one of the most essential requirement for them is to have a geotechnical report. Now, geotechnical, when the geotechnical requests for proposal are sent out, so a geotechnical engineer looks at the site and see what the request is, like what they're trying to build. And then based on that, they kind of come up with a plan that, okay, I'm going to do 5 boreholes to 10 meters, or I'm going to do 3 boreholes to 25 meters. It depends on different type of project. So I'm hearing a sound, sorry, I don't know. Okay. So it's when that proposal is accepted, first thing that geotechnical engineers do is place a first call or first call clearance in Alberta. It's or in Canada in general. When before you drill, before you dig a hole, because there are so much pipelines going all over the country, so they place that first call to make sure that they are not going to hit anything or have, that's required. So it's also a free service. A lot of times in a already developed land, there are electrical lines, etc., going through, and in order to locate those, the geotechnical engineer also hires a private locators. So it's important. Safety is very important because we don't want nobody to get hurt, and that's what the first thing that geotechnical engineers do after they get the project. Then they organize the field work. What, like I talked about. Okay, we will drill 10-meter holes. We'll do SPT every meter or every 5 meters. We'll collect samples every meter, and then we will take those samples to the lab for analysis. And based on those lab results and SPT data and field data, the geotechnical engineer performs the calculations and prepares reports, which goes to the different clients. Now, how there are different types of drill rigs. I mean, there are hundreds of types of drill rigs all over the world. Here are a kind of some of the very common drill rigs that are used in North America. And I'm going to share a couple of videos about this drill rig operation. So next one, kind of talk about type of drill rigs and drilling techniques. So here it is. I hope you can hear it properly.
The 4 most common drilling techniques: solid stem augering with the open hole method, hollow stem augering method, the wash boring method, and the casing method. It will also cover the basics of pushed and driven samplers. There are a number of types of drill rigs available. Some of the most common are large truck-mounted rigs, sometimes called highway rigs, off-road track-mounted rigs, and trailer-mounted or portable rigs. Different rigs are suited for different site conditions and different drilling and sampling methods. The large truck-mounted rig is the most versatile and one of the most common drill rigs used. However, it can only be used in situations where it can be driven onto the site. The process of drilling is similar regardless of the type of drill rig used. First, we position the rig over the location where we wish to drill. Then we erect the drilling boom or mast and make sure it's vertical. A drill head mounted on the boom is the mechanism used to perform the drilling and sampling operation. The drill head provides two motions to aid in drilling. A torque can be applied to rotate the bit, and a vertical thrust can be applied to raise and lower drill bits and other equipment. There are many different drilling and sampling techniques we can use to investigate the subsurface conditions. One of the simplest is the open hole method using solid stem continuous flight augers. The flights on a continuous flight auger run the full length of the auger. At the tip of the auger is a cutting bit. The inset photo shows two different diameter solid stem augers with two different types of cutting bits. The auger is rotated and pushed into the ground by the drill head. The bit at the tip of the auger loosens the soil at the bottom of the hole, and the flights carry the cuttings to the ground surface. An engineer or geologist can estimate when new soil layers are encountered by observing the changes in the cuttings as they're brought to the surface. These cuttings can be collected as bulk samples. However, they are low-quality samples because they're completely disturbed by the cutting process and because soil from the upper layers can contaminate soil from the lower layers as the cuttings are carried up the auger flights. When the boring reaches a depth where a higher quality sample is desired, the auger is removed from the hole to make room for the sampling equipment. In this method, the borehole must be able to stand open without support, which is why we call it the open hole method. When we wish to take a sample, we replace the auger bit with a sampling tool or sampler. Nearly all soil samplers consist of some sort of hollow tube which is inserted into the soil to retrieve the sample. There are many different designs of samplers to suit different soil conditions, but the basic process of sampling is similar for most of these samplers. The sample tool is lowered to the bottom of the boring and then pushed into the soil below the bottom of the boring. When the sampler has reached its full depth, the rods are twisted to shear off the bottom of the sampler, and the sampler containing the soil sample is retrieved from the boring. The sample is then stored for later analysis and testing. The sampling tool is replaced with the auger, and the auger lowered back down the hole. Augering continues until we reach a new layer where we wish to take another sample. The auger is then retracted from the hole and replaced by the sampling tool, and another sample is taken using the same process. When the soil is very stiff or dense, it's not possible to use a push-type sampler. In these circumstances, we use a heavy-walled sampler that can be driven into the soil using a drop hammer. The process is similar to retrieving a push-type sampler, but uses different equipment and a different sampler. The open hole method only works if the soil is stiff enough and strong enough to remain open after the augers are removed. While it is often possible to use the open hole method, many times the soil is not able to maintain an open hole for sampling. If the soil is soft, it may squeeze into the boring when the augers are removed. This often happens in a soft clay layer. If the soil is a clean sand with little or no cohesion, the soil at the sides of the hole may cave or fall into the boring. This is particularly a problem when drilling in sands below the water table. When squeezing or caving conditions occur, we must use a different drilling method that will support the borehole during the sampling process. One method that can be used in caving or squeezing soil conditions is the hollow stem auger method. In this method, we use a continuous flight auger as in the open hole method, but in this case, the auger stem is hollow. The bit in the center of the auger is retractable and can be removed through the hollow stem. The inset photo shows a hollow stem auger and its retractable center bit. For illustration purposes, the center bit has been removed and is shown next to the hollow stem auger. During drilling, the center bit is inserted inside the hollow stem. The augering process proceeds in the same fashion as with the open hole method. When we reach a depth at which we wish to take a sample, we stop augering, detach the center bit from the auger, and remove it.
Okay, just give you a demonstration of how these samples are taken with the drill rig. So there's a second video, but I'll skip it because of the time. I'm looking at the time, so it just talks about the same about the drill rig. So after the sample is taken, it goes to the lab similar to this one here, and we do very common soil tests. For example, moisture content is done in every level, and we pick geotechnical engineer looks at the description of the soil, and based on that, they kind of decide how many outer break limits they're going to do, how many hydrometer, grain size analysis, CBR test, or soil soluble sulfate test is very common in Alberta, and in Canada. Typically, we do sulfate tests to see what type of cement needs to be used. So because it's sometimes below the water table, the foundation. So here's, I just wanted to share some videos with you, kind of how these couple of these very common soil tests are done. So here is one technique that's just a quick overview.
Zero the scale and place a clean, dry sample container with the lid on the scale platform. Record the tin number and the tare or empty weight of the container, including the lid. Obtain a representative moisture content specimen and place it in the sample container. Immediately cover the tin with the lid. Zero the scale and place the sample on the scale platform. Record the tare plus wet weight of the sample. Remove the lid and place it below the sample container. Put the sample, container, and lid into the oven. Dry the sample to constant mass at a temperature of 230 plus or minus 9 degrees Fahrenheit. Constant mass means that the change in mass is less than 0.1% after 1 hour of drying. If the sample contains gypsum or has a high organic content, dry it at 140 degrees Fahrenheit or use vacuum desiccation. Remove the sample, container, and lid from the oven. Immediately place the lid on top of the container to prevent the sample from absorbing atmospheric moisture. Allow the sample to cool to room.
Sorry about that. I don't know. Okay, let's see here.
Zero the scale and place a clean, dry sample container with
Sorry about the technique.
And lid into the oven. Dry the sample to constant mass at a temperature of 230 plus or minus 9 degrees Fahrenheit. Constant mass means that the change in mass is less than 0.1% after 1 hour of drying. If the sample contains gypsum or has a high organic content, dry it at 140 degrees Fahrenheit or use vacuum desiccation. Remove the sample, container, and lid from the oven. Immediately place the lid on top of the container to prevent the sample from absorbing atmospheric moisture. Allow the sample to cool to room temperature. Zero the scale and place the cooled sample container on the scale platform. Record the tare plus dry weight of the sample. Calculate the moisture content by dividing the difference in the wet and dry weights divided by the dry weight and report to the nearest 0.1%. Note that for soils, the tare weight.
So thank you. That's just a very basic test that we do as a geotechnical engineer in the lab. And here is just a quick overview of what the hydrometer test is, how the hydrometer tests are done, and what is mean. Just a quick overview.
So this week we covered particle size distribution, and we used a hydrometer method to determine our texture of our soils. Okay, so what you did in lab this so it breaks up those soil aggregates, so the sand, the silt, and the clay aren't bound to each other in aggregate form, and that way we can get more accurate readings of in our sedimentation jar, because if they are aggregated, things will settle out faster than we want them to, so we really want to coat all of the soil particles with SHMP. So here we'll add 25 mils of SHMP. And now we're going to add 100 milliliters of water to this jar. So in here we have our soil, the SHMP, and 100 milliliters of water. And now we need to shake it vigorously for 3 to 5 minutes. Vigorously shaked our solution. We're now going to add it to our sedimentation jar, so we'll take the plunger out, add our solution to this sedimentation jar. You want to be sure whenever you're doing this in the future that you rinse out the inside, so that you want to get everything from your shaking jar into your sedimentation jar. Use a plunger to resuspend everything in the sedimentation jar. And then as soon as I take this out, Amy is going to set in the hydrometer and time for 40 seconds. 40 seconds. That's our reading. This reading gives us the percent of silt and clay that's in solution, because after 40 seconds the sand has settled out and only the suspended clay particles and silt particles are what are pushing up on the hydrometer. So this reading we will use in our future calculation. Our next reading is on an hour and a half, so we'll see you at an hour and a half. So it's been an hour and a half. So what we expect to be suspended is the clay, whereas the silt and all the sand particles have settled.
Okay, thank you. I hope you guys can watch the video properly and sound is okay. So the next slide, what is the important section of the geotechnical report? The geotechnical report, you would see that first it talks about the project description and site conditions, very important information for everyone involved. And then it talks about the investigation procedures, what procedures are used to perform the investigation, like how many holes, where the holes were taken, and how deep were they, and what type of depth the samples were taken. Then it talks about soil condition, like the soil, is it sandy, is it silty, or is it clay till? Clay till is a very common term in the Western Canada, in Alberta and British Columbia. Then it kind of inserts the lab results, like we just showed some of the lab result procedures. So those lab tests are recorded in a form, and those forms are included in the report. Then very important information is the groundwater condition. So where the groundwater is. Typically what we do is we install a piezometer, most of the projects, if the budget allows, and then the technician or a geotechnical engineering training or geotechnical, they go to the site and reads that piezometer after a couple of weeks to get where the water table is, or even it can be read throughout for like months to see where the water table sets, because it's kind of water table fluctuates depending on the season, depending on what's going on in the surrounding areas. Then very important information if you're in the cold country, where the frost level is. Now frost level could be different for different parts of the country. For example, here in St. Albert area, cross level is somewhere around 2 meters. Then we talk about the foundation recommendation, like we give them different options of foundation that can be used or built based on the process description of soil condition. For example, it could be shallow foundations such as footings. So we give the parameters for that. And then we give a parameter for deep foundation such as piles. The deep foundation could be a bit costly, so a lot of times if the project doesn't require deep foundations, the clients tend to go with footing foundations. Also, very common feature or for recent years is the screw pile. So we also give the clients the screw pile options. Then if the project has parking lots, etc., so we give them, what type of payments can be used. We give them both asphalt or concrete parking payments. But we don't have all the information at the time. We don't have ESOL values and all those information. So we just kind of give them a very preliminary design parameters. Then it also talk about earthworks, like what does it require? What does it require to be removed and replaced? If it's like Fort McMurray, there is a lot of organic material, or so organic material is not very friendly or not very suitable for building purposes. So that organic material has to be removed and replaced. So we can give them guideline how that can be done and what type of compaction required. Now, recently, radon consideration is very common since 2000, I believe 2014 in Alberta. So anytime there's like commercial properties or dense buildings, like density-wise, high-density building, for example, townhomes, etc. So there is radon consideration. Radon has to be mitigated. Then, of course, it has at the end all the bells and whistles of the project. Now, geotechnical engineering is not completed as soon as the geotechnical report is done. And Angela, how are we doing with time?
You're doing fine. You've got lots of time. So keep going.
Okay.
Yeah.
Okay. So geotechnical engineer, when the project goes into construction, the geotechnical engineer also gets involved in the geotechnical testing and monitoring of that, what they talked about in the report, make sure that it complies during the construction method. So geotechnical engineer observes and records if the pile foundations are that every whole team decided to go with. The geotechnical engineer makes sure that the pile foundations are at the right strata and it has the proper strength and it meets all the expectation that was initially assessed in the geotechnical report. Then if it's footing foundation, like you can see, these footings are like sometimes 10 meter deep or sometimes 6-7 meter deep. This one, so the geotechnical engineer makes sure that they go and check the footing foundation. It's free of debris. It's the condition that they've anticipated in the geotechnical report. So also when the like organic material or the soft soil, they're removed and replaced with suitable fill. This is something that also falls under geotechnical engineering and material engineering field. Like we check the compaction. This is just a quick video so you can understand how it's done.
standard counts. Now I need to know how to actually run this gauge.
Okay. Well, before you're ready to take a measurement, when you get to the job site, you'll want to find out a few things about the material that you'll be testing. So talk to the job foreman or superintendent, ask them what kind of material it is you'll be measuring, what the layer thickness is of that material, what the specs are for the job, like the percent compaction that you'll be needing to achieve, and the target for the material, the target density, and if it's a soil material, the target moisture percent. Okay? Set your gauge measurement count time to at least 1 minute or longer if you can. Also set the proper mode, the soil mode or the asphalt mode in the gauge. Soil mode would be for materials like clay, sand, aggregate, things that have moisture in them that helps the compaction process. Asphalt mode would of course be for asphalt material or non-cohesive aggregates.
I see. Okay, so every day I need to change these settings in this gauge?
Not necessarily. Okay. So the 1 minute count you'll probably use all the time. The soil or asphalt mode, maybe you'll change it, maybe not. Just depends on your job site.
Sure.
Okay.
Okay.
So, based on the layer thickness, you'll determine what kind of measurement you're going to take. So there's backscatter and there's direct transmission. Backscatter would be for soil, asphalt, any material placed in layers of 4 inches or less. Okay. Direct transmission is for anything that's placed in a layer of over 4 inches. A 4-inch layer can go either way. You can do backscatter or direct transmission if it's 4 inches. But more than 4, you'll definitely need to do direct transmission so that you can measure the whole layer from the bottom up. Okay. So there's very little prep, surface prep for a backscatter measurement. So the gauge just needs to be sitting in good contact with the material. So one way to check that is to press on the corners and see if it rocks. If it doesn't rock, you're pretty sure you've got good contact.
Good.
Next thing is to just lower the handle, seat it in the notch, go past the notch, and then just press the start button and then take a step back.
Okay.
Wait the 1 minute count time. Once it's done, step forward. First thing is to raise the handle, so you're shielding the source, and record your test results on your sheet, or better yet, press the store button so that the results are stored in the gauge memory if your gauge has that capability.
Wow, that's really simple.
Yeah, backscatter is easier. Now, if you're doing direct transmission, there'll be a little bit more prep work.
Okay.
So you'll need these accessories.
All right.
Okay, so there's the scraper plate, which you can use to smooth the site if you need to.
Okay, let me try that.
Yeah, if you need to. You want to have a nice smooth site, again, just like the backscatter. Okay, then your extraction tool goes over the tube.
Gotcha.
And your drill rod then goes in the tube. Okay? Don't forget the extraction tool. You'll have trouble pulling the drill rod out. Okay, so now there's marks on the drill rod every 2 inches. So this is a 6-inch layer of soil. We'll drive it to the 6-inch mark. So I believe that's 2, 4. This one's the 6-inch mark.
Oh, okay.
Yeah, so third one from the bottom.
Gotcha.
Now notice there's actually 2 inches extra built in, which is on purpose. So if you're driving it to the 6-inch notch, you're actually driving it 8 inches in the ground.
Okay.
So go ahead and drop it to 6.
Okay.
There you go.
Here we
Go
go.
ahead and grab the extraction tool handles.
Okay.
And pull straight up. And then best thing to do is to mark the front half of your plate. That way you'll have a footprint to set the gauge inside. So the front half, like a little bit on the sides is good, giving yourself a template to set the gauge inside. That's perfect.
All right.
Move the plate out of the way. It takes a little practice, but I can help you out. And we'll put the gauge inside that footprint. Right inside there. And lower the handle till you get past the 4-inch notch and then seat it in the 6-inch position. Next thing you want to do is push the gauge this way. It won't move much, but it might move a little. Then press your start button and again take a step back while it counts.
Okay.
Once it's done, you'll hear the beep and step forward, pull the handle up and up in the safe position, and go ahead and record your results or store them in the gauge.
Great.
So not too difficult.
Yeah.
If you're not taking another reading right away, you'll want to go ahead and store the gauge in the vehicle locked up so it doesn't get lost or stolen.
Great. That's super straightforward. Thanks a lot, Robin.
No, you're welcome. Okay, a couple questions that we got as a result of the last video. What if my standard count just won't pass? And that's a common question I get. Remember, the pass.
Thank you, guys. So that's what we do, how we do the compaction test. When almost every site requires that. It doesn't matter if it's a road structure, bridge structure, high-rise, commercial building, even housing development sites like whole subdivision. They have a lot of cut and fill associated on those sites. So another thing we do very common is the concrete testing. So the concrete typically are specified like 30 MPa or 45 MPa or 50 MPa. And CSA guideline, typically most of the design criteria is for 28 days, but a lot of times they require the strength to reach at 56 days. So geotechnical engineering representatives go to the site, follow CSA guidelines to cast the specimen. Those specimens are moisture cured or properly cured per CSA guidelines to test it, and at different age groups. Like some of them, what typically we do is 7 days, 28 days, and a 56 days, just to see the curve where the strength is. So typically, most of the specifications are specified at 28 days. Like for example, if it's 30 MPa at 28 days, so we do 2 specimens. We break 2 specimens in this machine and see if the strength would reach that. So this is one of the common things we do. We also do footing inspections, asphalt tests, etc. So there are all those geotechnical engineer actually from the initial stage to all the way to the completion of the project, they're involved. Now I hope you have enjoyed the presentation. It's just a quick one. I wanted to. It's a very large topic. So typically, when I do for students in different universities, it's about two hours. So I had to squeeze it in within 30 minutes because that's what it allowed. So now I will take questions if anybody have any.
I do have a question.
Yeah.
What has been one of your most challenging projects that and what did you have to do to be able to overcome some of the challenges that you had with a particular project?
So one of the very challenging projects that geotechnically we had was at Suncor site. Suncor is a oil sands company in Fort McMurray. So they have very poor soil conditions, and they needed to build a very heavy structure for froth treatment. So we had to come up with a foundation design that's going to be in limestone, and limestone were about between 28 to 30 meters deep. So we had to, and it was weathered limestone. So we needed to design rock socket piles, and it was kind of challenging to go into and drill those locations because of the muskegs and difficult conditions to move around those sites. Thank you, Angela. It was a very good question. Oh, sorry. Okay.
So does anyone else have any questions that they would like to ask? I'll just give you a minute. You can either use the chat box or you can unmute your microphone and ask a question.